Welcome back everybody to another video lecture. This is going to be part 3, describing the periodic table. Remember, for those of you in honors chemistry, this is going to be chapter 5 for you, but for my regular chemistry students, this is chapter 6. In this lesson, and probably I'll have to make a 4th part as well, we're going to describe the trends among the elements for atomic size. We'll definitely get to that in this video. And then we'll also talk about how ions form. I'm not sure if we'll get to this last part about the trends of ionization energy, ionic size, and electronegativity. So the first trend that we're going to talk about is this trend in atomic size. So measuring atoms is pretty tough because while we can see atoms, we really can't see inside of them. So the problem is, where do we start measuring them from? And scientists have ingeniously figured this out. So at first, this question came about because the electron cloud doesn't have a definite edge. So are we going to measure from one side of the cloud to the other side of the cloud? Well, there's no definite edge there. And they get around this by measuring more than one atom at a time. So when we measure the atomic size, we actually look at diatomic molecules, and we'll measure from the center or the nucleus to the other nucleus, and then we'll divide this in half and we'll just get the radii. So we sometimes talk about atomic size. You might hear it referred to as atomic radii. So we measure the atomic radius, and this is 1/2 the distance between the two nuclei of a diatomic molecule. Now, with all of the periodic trends that we're going to talk about today, they're influenced by 3 main factors, so keep them in mind as we talk about them. The first one is the energy level. So the higher energy levels are further away from the nucleus. So I'm hoping you remember, here's our nucleus. Here would be like level 1, energy level 2, 3. So obviously we're getting further and further away from the nucleus as we increase our energy level. The second thing to take into consideration is the charge on the nucleus. So how many protons are there in the nucleus? Because the more protons, the stronger the attraction they'll be. I almost think of when we increase the number of magnets, or the number of protons, we're like making a bigger magnet. So it says more charge pulls electrons in closer, and remember, positive and negative attract each other. So it pulls it in tighter. So like the magnet, these positive charges get stronger and pull these in closer. And then the third thing we're going to talk about is this shielding effect. Basically kind of blocks this positive and negative attraction. So more specifically, what do these 3 things influence? Well, when we're looking at trends among a group, and remember a group is going down, the things that we're going to notice is energy levels and shielding. And this makes sense because you've got 1, then 2, then 3, so it's getting bigger and further away. And then the other one that we need to worry about is nuclear charge, and these have an effect on the periods or the rows going across. And obviously if I have an element here and an element here in the same row, this one is going to have more protons, so it's going to have a larger nuclear charge because it has more protons in it. So the first thing that we want to talk about when we talk about atomic size is the group trend, or what's happening as we move from the top down to the bottom of the group. So it says as we increase the atomic number or go down the group, each atom has another energy level, so the atom gets bigger. So remember, we have 1 energy level here, 2 energy levels, so the electrons are even further away from the nucleus. This one will have 3, so even further away, and so on as we move down the group. Now the trend for atomic size as we move across the periodic table, or we go through the period, it says that going from left to right across the period, the size gets smaller. Electrons are in the same energy level, but there's a stronger nuclear charge, and the outermost electrons are pulled in closer. So if I was to look at a sodium atom, it's going to have a certain strength to it, but if I look at an argon, it's going to have even a larger strength to it, a larger nuclear charge. And the reason it has a larger nuclear charge is argon has more protons than sodium does. And since the charge down here is stronger, it pulls the electrons in even closer to the center of the nucleus than the nucleus of a sodium atom. So the trend that we observe, I realize it seems maybe counterintuitive to you, But the idea is that these are stronger nuclear charges as you move across the table. So as it gets stronger, it pulls those electrons in closer to the nucleus. It's pulling them in closer to the nucleus. So an excellent way to observe the trends on the periodic table is to go ahead and graph them. So here we are looking at the atomic radius and then the atomic number as it changes. So basically we're looking at each period going through the periodic table. So the first thing off, we start with lithium, and then notice as we move across the periodic table, the last element in that same period is neon. So neon has a smaller atomic radius than lithium does because neon has more protons, so its nuclear charge is stronger, so it's pulling its electrons in closer to the center of the nucleus, so neon is smaller than lithium. We can see the trend continues with other periods. We have sodium that starts off the period. Argon is our noble gas ends, so obviously argon is smaller in atomic radius than sodium is. Next period, we have potassium. Then if we follow it along, of course we have a few exceptions to the rule, but remember we had some exceptions with our electron configurations as we went through this, dealing with the d orbitals. But we notice here that krypton is smaller than potassium, and then the trend continues even though there's a few hiccups along the way. Some compounds are composed of particles called ions, and we've talked a little bit about ions in the past, and we've said that an ion is an atom or a group of atoms that has a positive or negative charge. Atoms are neutral because the number of protons is equal to the number of electrons. Positive and negative ions are formed when electrons are transferred. That means they're gained or lost between atoms. So before we move on, I just want to make sure that you're clear on how ions are formed. So remember when we talk about protons, we say that they have a positive charge and electrons have a negative charge. So normally if an atom is neutral, they have an equal number of protons and neutrons. But obviously if I have more of one than the other, the charge is either going to be positive or negative. So a classic example to talk about is oxygen. So if oxygen has 8 protons and 8 electrons, if I add them up, because remember this has a positive charge and this has a negative charge, so our overall charge would be 0, and this atom of oxygen would be neutral. But in this next example, if I have oxygen again, so I'm going to have 8 positive charges. Then if I say I have 10, I gain 2 electrons. Now when I take my positive 8 plus my negative 10, I'm going to have an overall charge of negative 2, and I would say in this case that I had a negative ion. We'll also learn that this is referred to as an anion a little bit later. Another example here is if I have oxygen again, so with 8 positive charges, and let's say for some reason it lost some electrons, so it would have less than it normally would. Let's just say it lost 1 electron. Well, if I take positive 8 plus negative 7, I come up with a charge of positive 1, so I have a positive ion here, and this is sometimes referred to as a cation. So this is how ions can form. Normally we can think of having just neutral atoms, but on occasion atoms can gain electrons and end up with a negative charge, or atoms can lose electrons and end up with a positive charge. Now some trends that I definitely want you to keep in mind, and you'll really need them for the next chapter, is that metals tend to lose electrons from their outer energy level. And so here we're saying that sodium loses 1, there's now 11 protons, and now you only have 10 electrons. Thus we have this positively charged particle forming a cation. So I just did a little math off to the left over here. Again, we've got 11 positive charges plus 10 negative charges. So now we have an overall charge of plus 1, and since it's positive, we call it a cation. So the charge is written as a number followed by a plus sign. So here's our sodium. We would give it a little superscript plus 1, saying that it was an ion. And sometimes we'll even just leave this 1 off and it's assumed that it's 1 plus. So now we'd say that this is a sodium ion. On this slide, I just want to go ahead and give you a little background as to why sodium wants to lose its 1 electron, or this is the trend that we see in metals. So here I'm going to use a Bohr model, and please remember that a Bohr model is not a fantastic representation of where electrons currently are. In fact, we now remember use the quantum mechanical model, and we have these s and p and d orbitals, but I think it does a good job of showing you why this happens. So remember, the first energy level only holds 2 electrons. And sodium has 11, so we need to plug in 11 electrons. So the next energy level can hold 8. And then in the last energy level, why it can also hold 8, we're just going to say that it's going to hold 1 in this case. So remember, the goal of every atom is that they want to obtain what we call noble gas configuration, and that means that they have a full energy shell. Well, if we look at the 3 energy levels here, we can obviously see that the third energy level is not full, but the second energy level is full. So in order to make this third energy level full, we would need to gain 7 more electrons. Or sodium could lose this 1 electron and still have the next energy level be full, and so it would obtain the noble gas configuration for neon. So the trend here that we're going to see is sodium thinks, and I want to put thinks in quotes here, it thinks that losing this 1 is going to be easier than gaining 7, so when it does that, it obtains the noble gas configuration of neon, just like I said it would. That energy level is now full because we've lost that 1 electron. Now the next trend that I want you to know about is that nonmetals tend to gain one or more electrons. So the example we have here is that chlorine will gain an electron. So normally it has 17 protons, but if it has 18 electrons, we now have 17 positive charges and 18 negative charges, so we end up with an overall charge of -1. So we now call this a chloride ion, and again, since it has a negative charge, it's called an anion. So on this slide, I just want to show you why chlorine would want to go ahead and gain an electron rather than lose them. So again, I'm drawing this Bohr model here as more of an example to show you why this happens. Remember again, all elements want to obtain that noble gas configuration, which means that they want to have their outer energy shell full. And when we look at chlorine here, we can see that in the outer energy shell that there is 7 electrons. So chlorine can either lose all 7 electrons, or it can gain 1 more to obtain that noble gas configuration. And chlorine then, because it seems easier, it's going to add this, and now it's going to have 18 electrons and a full outer shell, so it's going to more closely resemble argon. I realize I'm just about out of time, so in the next video we're going to go ahead and discuss ionization energy, and hopefully we'll get to electronegativity.